In this third segment of the titration of a weak acid with a strong base, let's take a look at how one determines where the equivalence point is. That is to say, how many milliliters of the sodium hydroxide have to be added to reach the equivalence point, and then as a second question, just what exactly is the pH at the equivalence point equal to? Now, the first thing to recognize about the equivalence point is that it is the point where the number of moles of original acetic acid are now equal to the number of moles of sodium hydroxide that we add. That's the equivalence point. It's when equal molar amounts are available, and the acetic acid at this point has been completely consumed, as there are just enough acetic acid molecules to neutralize the added number of sodium hydroxide moles. Okay, now we already know the number of moles of acetic acid. From previous calculations, we know that there were 0.0500 moles of acetic acid, and therefore that is the same number of moles of sodium hydroxide that we have to add. The question is, how do we get that number of moles of sodium hydroxide? And the calculation is really very easy. A rearrangement of our molarity definition tells us that volume is equal to moles divided by molarity. And moles in this case, 0.0500 moles divided by the molarity of the sodium hydroxide, 1.00 molar, tells us that we need 0.0500 liters, or 50.0 milliliters of sodium hydroxide. Okay, so we can reach the equivalence point by titrating in 50 milliliters of sodium hydroxide. In doing so, we'll have provided just the same number of moles of sodium hydroxide as there were original acetic acids, and the two will completely neutralize each other, as is the definition of the equivalence point. Another thing to keep track of here, too, though, is that as we'll soon be doing some ice problems, the total volume now is actually equal to not 500 milliliters, but 550 milliliters, or 0.550 liters, so something good to keep in mind. Now, at the equivalence point, things change a little bit, because the amount of CH3COOH, its concentration, is now equal to 0. And that is because all of these acetic acid molecules have been wiped out or neutralized by the sodium hydroxide that we've actually put in place. But there is a significant amount of acetate ions that have been produced, and as you should recall, the acidic form is acetic acid, and the conjugate base of acetic acid, the acetate ion, is what we have here in great abundance, and that certainly isn't equal to 0. And the fact that we have no acetic acid present here at the equivalence point tells us that we have now a weak base equilibrium that we have to consider. And so at the equivalence point, what we have to do is consider the weak base equilibrium. And the weak base equilibrium looks like this. We have the CH3COO-, the acetate ions that are there. They react with water in equilibrium. Now with hydroxide ions, that's how weak base equilibria differ from weak acid equilibrium. And then we have the reappearance of the CH3COOH. The acetic acid shows up as a product in this case. And in this case, K sub B, the weak base equilibrium constant, is K sub W divided by K sub A. And we have numbers for this. It's 1.0 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5th. And you do the arithmetic, and what you find is that this weak base equilibrium constant is 5.55 repeating times 10 to the minus 10th, a very small equilibrium constant. All right. Now, what we have to do is move forward here with the actual ice problem. And as part of the ice problem, we're going to need to calculate the initial concentrations of things. Now, if you refer back to the previous problem, with every 0.01 moles of sodium hydroxide we put into the solution, 0.01 moles of acetate ions were produced. And so in this case, we've put in 0.05 moles of sodium hydroxide, and we will have a total at the end of the neutralization part of the problem of 0.0500 moles of acetate, and the new volume will be 550 milliliters, 0.550 liters, and this concentration comes out to be 0.0909 molar. Repeating, we'll assume that there are no hydroxides present to begin with and that there are no acetic acids there as well. And with nothing appearing on the left-hand or on the right-hand side, we know this is a reaction that has to shift to the right, and we're going to see a minus X here, a plus X here, and a plus X here. Okay. Now, that leaves us with equilibrium concentrations of 0.0909 minus X and X and X. And then we've got some arithmetic to do. Okay, we've got the equilibrium constant expressions. The law of mass action tells us that K sub B is going to be equal to the concentrations of the products. It's a weak base equilibrium, and so we've got these as the products, and the reactants, actually the concentration of the acetate ion. And we can put in the numbers, 5.55 times 10 to the minus 10th is the equilibrium constant. And we have expressions for the hydroxide ion concentration. Why, that's just X. And the acetic acid concentration, that's just X as well. And then we also have an expression for the acetate ion, the only reactant, 0.0909, and that'll be minus X. We'll go ahead and make the assumption that this X is approximately equal to 0. A very valid assumption in this case, since the equilibrium constant is 5.5 times 10 to the minus 10th, minus 10, a very small number, and seems quite reasonable to make that assumption. We should check that a little bit later on. If you do this, and you solve now for X, you'll find that X is equal to 7.1066 times 10 to the minus 6th, and I've done a 5% check on this. It comes out to be 0.008%, a very small amount in comparison to the 0.0909, and so we're quite happy with that assumption. Now, at this point, you've worked out a K sub B problem, and you've really worked hard to get this far. Don't lose it in the end. In our case here, X is actually equal to the hydroxide ion concentration. Now, that's important because when we take the negative log of this value, why, we're not going to have the pH, we're going to have the pOH. And so the pOH is the negative log of this value, the hydronium ion concentration. And doing so, we get a pOH of 5.14, and subtracting that from 14, we get that the pH at the equivalence point is equal to 8.85, I guess, with 2 decimal places, 2 significant figures throughout the problem. And so in this third segment, where we've now determined the location in milliliters of sodium hydroxide of the equivalence point, namely 50 milliliters needed to get there, the pH at the equivalence point is considerably higher than it has been up to this point, and will soon go even higher still as we continue to add sodium hydroxide.